Yeah. Am I audible?
Yeah, you are audible.
Thank you. I, Dr. Manush Laik, on behalf of the Department of Chemistry and Chemical Society of the Department of Chemistry of Bankura Christian College, welcome you all in this international webinar titled Ultrafast Look at Chemical Processes and a Peep into the World of Molecular Magnets. A very good morning to one and all. Before we start our inaugural session, I request all the participants to kindly mute your microphones. At the end of every lecture, you will have the opportunity to unmute and ask questions during the question and answer session. You can also type your questions in the chat box at any time during the lecture session. I will bring them up during the question and answer session. Now I request our principal sir and patron of this webinar, Dr. Fotik Boron Mondol, to kindly deliver the welcome address. Sir.
Sir, your microphone is muted. Please unmute your microphone.
Thank you.
Unmute, sir.
This is my pleasure to be the one of the speaker in this international webinar entitled Ultrafast Look at Chemical Processes and a Peep into the World of Molecular Magnets, organized by the Department of Chemistry of our college in collaboration with the Chemical Society of Department of Chemistry. In fact, first of all, I wish to extend my sincere thanks to all my colleagues and teachers of the Department of Chemistry for organizing such an international webinar on a attractive topic. I think that our invited speaker, Dr. Joydev Gowda from Ghent University, Belgium, and Dr. Jahur Alam Mandal from the Bhava Atomic National Institute of Mumbai, India, will enrich us in the particular topic of molecular magnets. In fact, I am a student of biology and I know very little about magnetism and its effects on biological organism. However, I have worked some preliminary studies on the magnetotactic bacteria and effect of Earth magnetic field on invertebrates and other higher groups of vertebrates, including human. This was real bit interesting to me, but our field includes the genetic components, environmental components, etc. Mainly, I think you are going to address the magnets, molecular magnets, the component from chemical angle, and it would have significant value to the academician, to the researcher, as well as to our students. They will be stimulated to go into the deep of the mechanism of magnets. I think and I wish every success of this webinar, and I request my students to interact with the renowned persons who will speak as a resource person in this webinar. With these few words, I welcome you all again to make the webinar a successful event. Thank you all.
Thank you, sir, for your words of encouragement. Now I request Dr. Shamir Kumar Rai, President of the Organizing Committee and ex-Head of the Department of Chemistry, to deliver the keynote address. Sir.
Respected Dr. Pratik Baron Mondol, Principal, Bankura Christian College, Honorable Resource Persons, Dr. Joydev Gowda, Ghent University, Belgium, and Dr. Jahur Alam Mondol, Ava Atomic Research Center, Mumbai. The teacher participants of different colleges and universities, and the student participants of different institutions, including Bankura Christian College. A very sincere and warm welcome to everyone. On behalf of the organizing committee, and at the same time, on behalf of the Chemical Society of the Department of Chemistry, Bankura Christian College, I take the proud privilege to extend my hearty welcome to all of you in today's international webinar, Ultrafast Look at Chemical Processes and a Peep into the World of Molecular Magnets. In recent times, the research in chemistry has crossed the boundaries of different branches, emerging with a new dimension of understanding and widening its field of application. The aim of the present webinar is not only to visualize the newer aspects and impacts of the chemical studies, but also to take a stock of the past history, present status, and future directions of chemical research. Both the topics of today's webinar will highlight the recent developments in the field of laser spectroscopy and molecular magnetism to provide the participants with an updated overview, giving insights into their applications in different modern fields. Our first resource person, Dr. Joydev Gowda, who did his master's in chemistry from Vidyasagar University in 2009 and obtained PhD from IIT Kanpur in 2014. During 16 to 17, he was in Rutgers University, USA, and during 17 to 20, he did advanced research at Jakob University, Germany. Currently, he is associated with Ghent University, Belgium. He has authored more than 30 research publications in journals of international review. His research interests are the study of single molecule magnet, which is a forefront research area in coordination chemistry, having many potential applications such as molecular spintronics, high-density data storage devices, and magnetic refrigeration. Today, Dr. Gowda will discuss the basics of molecular magnetism and viable strategies, synthetic strategies. Our second resource person, Dr. Jahur Alam Mondol, did his bachelor's and master's in chemistry at University of Bardwan, and then he moved to the Radiation and Photochemistry Division, Bhabha Atomic Research Center, Mumbai in 2002. In 2009, he received his PhD degree on ultrafast dynamics in condensed phase at the University of Mumbai. During 2009 to 2011, he did his postdoctoral research on some frequency generation spectroscopy as a JSP. His current research interests are understanding the molecular and macroscopic interfaces pertaining to biological and environmental systems using the state-of-the-art laser spectroscopy. Professor Mondal and 50 peer-reviewed papers in international journals of repute, with more than 30 in the field of aqueous interface using some frequency generation and round spectroscopy. In recognition of his work in this area, he has been awarded the prestigious Young Scientist Award, or more appropriately, Discovery to Development was not an easy task due to enormous practical difficulties. Einstein had a unique and peculiar style of research. He made many of his discoveries by the force of sheer thought, commercially developed. The monochromaticity, directionality, and high intensity of laser beam have made possible wide range of investigations in various scientific fields such as physics, chemistry, biology, medicine, communication. The long history, the rich heritage, and the strong tradition of academic activities have been the most important elements in making the department one of the premier and potential centers for undergraduate education in chemistry. It is probably one of the very few undergraduate departments in West Bengal which undertook research program more than a decade ago, utilizing the very limited research level infrastructure available in the college during that time. The department has also started collaborative research work with some foreign universities, namely the Institute of Mineralogy and Technography, University of Vienna at Austria, the Department of Chemistry, the University of Barcelona, Spain, and department is now also going to start collaborative research work with Dr. Joydev Gowda of Ghent University, Belgium. The department teaching to arrange and organize lectures, seminars, discussions, and webinars for the diffusion and mentoring them based on their interest and need, to provide some financial aid to poor and needy students, to emancipate them in the light of education, and finally, to promote and encourage advancement of scientific and technical education. Of course, the fulfillment of these faculty members and the ex-students in India and abroad. The department has the proud privilege of having the contribution of many distinguished alumni. Nowadays, we all know that in the spheres of social behavior, scientific attitude is discount. The activities of the chemical society always help students in developing the right chemistry department and the chemical society are complementary to each other. I express my sincere gratitude to Dr. Joydev Gowda, Ghent University, Belgium, and Dr. Jahur Alam Mandal, Bhava Atomic Research Center, Mumbai, for being the resource persons of today's webinar in these difficult times of COVID-19 pandemic. I sincerely hope that their deliberations will not just be a string of words, but will be intellectually fruitful and stimulating, thus providing a powerful motivation and impetus to the students who will, of course, have absorbing all.
Your lecture has given us an idea about the lectures that we are going to listen. Thank you once again, sir. And now, just a minute. Now we are going to start our technical session. We have our first
Principal of the Bankura Christian College for giving me opportunity in this webinar, as well as Professor Somir Kumar Roy and Professor Santanu Mondol and Professor Manoglai and all other organizing committee. They are a fantastic webinar in online, and maybe it will helpful for all students, their future direction of chemistry, why they are learning chemistry or studying chemistry, and not only the study, but in the future application in the research. In the human application. So in this webinar, already Professor Roy introduced what I am going to talk. So I'm not going to discuss more, and I'm directly going to my presentation. So now I'm going to share my slide. One moment. Just a moment. So is there any problem for window sharing or no? It's okay. Yeah.
No problem.
So
Sir.
is this slide visible, sir?
Not yet.
Hello. Not yet
No
visible.
slide. Not yet. Yes.
Oh,
Now it has come now. Okay.
Now it's visible. Okay. So I'm going to talk about molecular magnetism. So before going to talk, I would like to just give the outline of my talk, that what I'm going to talk is fundamentals of magnetism and what are the single molecule magnets and how single molecule magnets developed, starting from 3D, 4F, 3D, and then 4F cluster, and finally I will conclude my talk. So what are the magnets? The magnets are materials that attract the metals, like lodestone or hematite, as a common example. And what is the basic principle of magnets? The magnets attracts the opposite poles and repels the like pole. When they closer, they can be attract more. How this magnetic force generated? The lines of force comes from North Pole to South Pole, and which is indicates the number of lines indicates the density of the magnet or strength of the magnet, how it is a stronger magnet. The the magnetic flux is the intensity in spherical and emit the magnetization. If we simplify this, then this comes from the mu equal to mu r into mu zero, where mu zero is the magnetic permeability, which is the one of the component can be said that molecule as a magnet or not. So based on this, if this permeability is 0 or near to 0, this is called diamagnetic. If it is greater than 1, then it is paramagnetic. If it is very much greater than 1, then it will be ferromagnetic. Now, what types of magnet? Magnets could be permanent or temporary. There are 3 types of magnets. It could be natural magnet, artificial magnet, and electromagnets. How magnetism generates? As we know, when the moving charged particle move around the circle, that's create the field. Like in atom, the electron when move the orbit, then generate a magnetic moment, which is called the orbital magnetic moment. And the direction of the magnetic moment is depends on the field or the magnetic moments depends on which direction is going. So if the number of spin are on the same direction, that is called magnet. If it is same number of spin in the opposite direction, that's called the diamagnet. Now, depending on the bulk material, magnets can be classified at the 4 major classes, like a paramagnet, which is the hazardous spin. If it is same number of spin opposite direction, that is called antiferromagnet. If it is all spin are the same direction, that is called the ferromagnet. If it is partially cancel the spin momentum, that is called the ferrimagnet. There are another class of magnet which is called the magnetic frustration. Here you can see when the antiferromagnetic materials, they are the one spin cannot be coincide which direction it will going to couple. That is called the magnetic frustration. That's generally happens in the triangular unit. Now, question is that how we can characterize the magnetism. The magnetism can be characterized by basic is the magnetic susceptibility. What is magnetic susceptibility? Magnetic susceptibility is the degree of magnetization of the materials under applied field, where magnetic susceptibility denoted by chi. Chi equal to m by h, where is the magnetization m and h is the field. And if we simplify this equation by number of, then chi m is equal to mu square by 3 kT unpaired electron, and all other values constant and Boltzmann constant, temperature, etc. So if we plot this chi m t versus t, here you can see for the ferromagnetic substance, the momentum is decreases like exponential. For the paramagnetic substance, it is a straight line, and antiferromagnetic, which also decreases in decreasing temperature. But thing is that beginning of the paramagnetism defined by the Curie's law. In this case, Curie's law assumes that there is this is molecule are isolated and there is no magnetic interaction within the molecule. But this is not the actual case. In this case, then chi m should be proportional to 1 by T, where T is the temperature and K is the Curie constant, and C is the characteristics of the paramagnetic substance. But this equation valid when the h by chi t, this comes from the other parameter calculating, and if it is very small, then chi m proportional to C by T, it's valid. But if we plot this in the figure where chi m versus T, there you can see for the paramagnetic and ferromagnetic case, the exponentially decrease the magnetic moment, and for antiferromagnetic coupling, the continuously increase the magnetic moment. But this is not the actual case for the compound. Then Curie and Weiss law think that no, there is some interaction between the intermolecular, either intramolecular interaction between the magnetic cluster. So this equation must be modified. Then they modified that chi m is equal to C by T minus theta, where theta is the Curie-Weiss constant. If we plot in this case, then we see the paramagnetic substance where this is passing from the straight line, and the antiferromagnetic ferromagnetic, which is cutting from the negative axis, and ferromagnetic cutting from the positive axis. And this is actually we can see in this magnetic class compound. So for this case, so there is another also interesting distinct features for the magnetic substance is the hysteresis. Now, what is hysteresis? Hysteresis is that if we plot the magnetic compound, if we magnetize by under applied field, let us say in the zero field, the magnetic is here. If we applied field, it will be saturated. And if we removal of the field, then this magnetism still remains. This is the MR. This is called the magnetic hysteresis law. This hysteresis law generally shows for the ferromagnetic substance and ferrimagnetic substance. But thing is that depending on the hysteresis, like less than 1, it is the Gauss, it is called soft magnet. If it is very much greater than 500, it is called the hard magnet. So this hysteresis also can be measure some other techniques like physicists as well as chemists. Also, this can be shown by macroscopic, microscopic, and nanoscopic cluster. And as we are a chemist, we are interested on cluster or molecular cluster. This is called, like sometimes it's nano cluster, which is the assembly of multi-metal that possesses the many number of unpaired electrons. So now question is that what is molecule? As we know, the basic, we start from periodic table. There is the 3 groups of metal basically, but we have 4 also. The S block element and P block element in between the D block. This is called sometimes transition element, and also A block element, inner transition element. And what are the D block or transition element? Transition element, those D blocks are partially occupied by electrons. Now, what is interesting for the D block elements as a magnetic as well as the color, they are interesting. So what is coordination complex? The complex are composed by metal which is surrounded by ligands. What is the ligands? Ligands are the Lewis bases which donate their electron pair to the Lewis acid metal center. Now, this is generally the notation for the coordination complex. Just I show one example. All of the other students, I hope they know everything for coordination complex. And what is the coordination number? The number of ligands surrounded or donated around the to the metal center, which called the coordination number. Generally, coordination numbers are 2 to 12, but most coordination number are the common coordination number is 6. For this complex, this coordination number is 6 because there is 6 ammonia ligand donated to the cobalt center. The bond structure of these complexes are depending on their coordination number. If it is 2 coordinated ligand, that is linear. 3 coordinated, triangular, planar, tetrahedral, or square planar for coordination number, as well as 5 and 6. 6 is octahedral and 5 is trigonal, bipyramidal, or the square pyramidal. So the structure of bonding of these complexes can be introduced or discussed by the Pauling in 1932 by VBT, which is mainly in the hybridization concept. In this concept, if we consider, let us say, octahedral complex chromium 3, the D3 system, and the available vacant orbital for the hybridization are 3d z square and 3d x square minus y square, 4s and 4p. When the ligands come, let us say water comes, so then can donate the electron pair to the vacant orbital. It's from the D2sp3 hybridization, and which is perfect for the chromium 3 octahedral complex. And in this case, you can see there are 3 number of unpaired electrons, so it is paramagnetic. Let us see for another example like iron. Iron 3 octahedral complex, also same iron 3 D5 system, it is 5 unpaired electron. If it is from the inner orbital complex like iron hexacyanide 3 minus, so what happened here? Here you can see the hybridization is D2sp3, number of unpaired electron is 1. Yeah, if it is outer orbital complex for iron hexafluoro 3 minus, so you can see here is the 5 unpaired electrons, and it is the outer 4d orbital. So now this hybridization is not realistic. Why it is not realistic? Because first it's violate the above principle. 4d orbital is higher energy than 3d orbital. So in this case, we can say that all the coordination complexes does not obey the valence bond theory. If you see for nickel complex, nickel 2 or D8, octahedral, tetrahedral, and square planar, here you can see the tetrahedral complex, number 1 pair electron 2, it is paramagnetic. Octahedral complex, DsP2 hybridization, sorry, sp3d2 hybridization, also number 1 pair electron 2, but for square planar complex, it is dsp2 hybridization, it is diamagnetic. So what are the limitations of the VBT? So VBT actually not explain the spectroscopy of transition metal complexes, which is very important, as well as the low spin and high spin complexes, why it's formed, for like iron case or nickel case also, and the kinetic inertness that generally comes from the inner orbital or outer orbital complexes, as well as temperature dependent magnetic moment. That cannot be explained by the VBT theory. Then Hans Bethe and Van Vleck, they introduced the crystal field theory. This theory can be explained partially for the beautiful colors of transition metal as well as their magnetic properties. In this theory, they have assumed some assumption like the before VBT was covalent interaction, now CFT has ionic description. And in this case, ligands should be point charges, and the interaction between the metal ligand are purely electrostatic. So here we can look at how the orbital shape for this P and D. Basically, I have not shown the S orbital. You can see this is the 3p orbital shape and this is the 5d orbital shape. Let us consider for the free metal ion d orbital. If it is the 5d orbital, quantum number L equal to 2, and for this manganese 2 or iron 3 is equal to 5/2. So if you see the ground state configuration, the 5d orbital have 5 unpaired electron. This is called the degenerate orbital in absence of the ligand, because these all orbital have the same energy. So what happens if the metal ion are surrounded by the ligand? So if the metal ion surrounded by the ligand, so ligand has important role to split the d orbital, because for the p and d orbital, p orbital has the x, y, z directional, and d orbital, sum of the x, y, z direction, the x, dxy, dyz, and dxz, and dz square is the other direction, and dx square in the in between. So those orbitals are along the axis, those will be interact much more when ligands come along axis. And those are not along axis, they will be less interact. And simultaneously, there will be repulsive force between the ligand electron and metal d electron. So in this case, if you consider for octahedral complex, here you can see the 5d orbital are splitted in 2 different shapes, where 3 is the 3 orbital dxy, dyz, and dxz is T2g because of the triply degenerate orbitals. Here you can see this angular representation I'm showing, and here another is dx square minus y square, which is in between axis, and dz square, the EG axis. And this energy difference is called the octahedral energy difference. I will show you later. And let us now consider when, like say, iron 2 complex. If iron 2 complex, D6 system, octahedral case, if you see there will be, I have not shown the spin state, here will be the in the state is like 3D D6 system. So this is the, let us say no weak field ligand, then what will happen? Now this electronic distribution would be T2G4 and EG2. And here you can see the number of unpaired electron is 4. So this is paramagnetic. If it is strong field ligand like cyanide or ammonia, then it will be this T2G6 and EG0. And this is called diamagnetic. And this intermediate state here, it depends on the temperature, pressure, etc. And that spin state transition called the spin crossover transition. So I'm not going to discuss. So now, how is the octahedral crystal field? Here you can see the octahedral crystal field and also energy difference. So what determines the delta O? Delta O determines the octahedral crystal field energy. And this determines also how the ligand, it is strong field or weak field ligand, as well as the oxidation state of the metal, it is the low oxidation state or high oxidation state, that indicates. And what is the ligand spectrochemical series? The spectrochemical series is the set of ligands which is splitting the d orbital energy that comes from the d orbital splitting nature of this weak field as well as strong field. Here you can see the all iodide which have the lone pair of electrons, which is called weak field, and also the neutral ligand and cyanide as a strong field ligand, which can form the low spin complexes. Now, if we consider like iron hexaaqua 3+ and iron hexacyanide 3- complexes, what is the oxidation state of iron? Now, if we consider here, the charge is for first complex +3, and water is neutral ligand, so 0. Instead, if we get the +3, so iron should be the +3. And for the iron cyanide, as we know, cyanide is the -1 charge. So 6 cyanide is 6-, and here is the 3-. So if we calculate here, so iron is +3. And what would be the D count? As we know, iron 0 is D8 electron system. So if we subtract from the 8 by -3, then it will be 5. So iron 3 has D5 electron. And how will be the octahedral splitting diagram? This octahedral splitting diagram will be this. And this octahedral splitting diagram, now questions come, how the electron can be distributed. Now this electron distribution depends on also the pairing energy. If the pairing energy greater than the octahedral crystal field, then it will be the high spin complex. If the pairing energy is less than octahedral crystal field energy, then it will be the low spin complex. But then what will be the electronic configuration for this complex? So it will be T2G3 Eg2 for high spin, and for low spin it is T2G6 Eg0. This pairing energy also depends on the other factor. What? Now, the pairing energy is the energy to cause the pair of electrons in a single orbital. How it's? That is, the first is Coulombic repulsion, because if the electrons are occupied in the same orbital, there will be electronic repulsion. And that repulsion is going to decrease from 3D to 5D. And there is also loss of exchange energy when it is be singly occupied or doubly occupied by Hund's rule, maximum number of unpaired electrons. So that's called the exchange energy. How it would be? So this exchange energy can be calculated, is proportional to n into n-1/2, where n is the number of parallel spin in same orbital. So if we see here D6 high spin complex, the pairing energy would be 10, and for D6 low spin complex, it will be for same direction, here is 3, and another direction is 3, so 6. That's now question is that why iron 2 complex sometimes form low spin complex, but manganese 2 does not. So in this case, we can explain by the exchange energy equation. For iron 2 case, it is D6 system. So if it is high spin, here you can calculate the exchange energy. And for the low spin calls also, you can calculate the exchange energy. So loss of exchange energy from high spin to low spin would be 4. In case of manganese 2 case, also here you can calculate. So here will be 6. So that is why for the iron 2 complex, sometimes weak field ligand from low spin complex, but manganese 2 does not. Now, what are the if the molecules and inside molecules, there will be interaction with nearby atom, what will happen? That can be interaction by parallel or anti-parallel, and that we all know the wave function. So if it will be parallel spin, like orthogonality 90-degree coupling, so then it will be calculated by the coupling constant J, or it is called energy also. So if the difference from the ground state to excited state, it will be positive, then it is called the ferromagnetic, and that is the interaction. If it will be negative, then this is the strong interaction, antiferromagnetic interaction, like many examples, manganese oxide, copper oxide, that etc. So now here attention is what will be the isolated molecule, and now I'm going to talk about single molecule magnet. The molecular magnetism, which is the interdisciplinary field and link between chemistry, physics, and biology, and that is mainly design, synthesis, and their physical characterization for this isolated molecule. And this actually the fundamental building block in the molecular unit, not the atomic unit. Atom like iron is magnetic and copper it does not, but here it is the molecular unit. How can chemists do this magnetic properties or varying the magnetic properties? That is very simple. As we say also that the many transition metal and lanthanide, they are active, magnetically active. If we simply change the ligand system around the metal, what will happen if we change the ligand? That can change the spin state, their structure, as well as geometry, and also color. Now let us say like cobalt chloride, it is this blue color. If we hydrated the cobalt chloride, it will be pink color. If we heat it, then it will be the chain complex, also again the light blue color. If we add excess HCl, then it will be the deep purple color. So this is cobalt tetrachloride. If it is the reverse process, if we remove from chloride and then water, so it will come from the cobalt chloride dehydration state. Why these tetrahedral complex are more intense color than the octahedral complex? Because tetrahedral complex has no center of symmetry, as well as here electronic transition permitted by the selection rule. But in this throughout the case, the spin state would be remain same. So as cobalt 2 is D7 case, so that's unpaired electron number same. Now how can chemists change the spin state? Let us say more salt, iron 2 hexaaqua. So where it is a pale green color and high spin. If we add the phenanthrolene, it will be the red color and total number of unpaired electron is 0. So this is low spin complex. So if you vary the ligand, that can help to paramagnetic to diamagnetic case. So now classification of magnet, there are 3 different major classes of magnet, like purely organic molecule, like free radical molecule are magnetic property. Also the inorganic approach, like the metal alloy cluster or peroxide, as well as the inorganic approach combining with metal ion as well as the ligand. And we are interested only these metal inorganic combinations. So now coming the recent research in 20th century says that the low dimensional, that is 0-dimensional cluster are magnetically more important because that can be future application is high density data storage device, magnetic refrigeration, spring tonics, as well as their other applications like biology, and I will show last slide how magnet can be used for the future application. But in our traditional magnet, there is some demerits. What demerits? The traditional magnet has low density data storage, as well as we cannot the modification, their chemical modification, as well as solubility problem and optical property. So then people think that better than the conventional magnet, how we can develop their properties or improve their properties. So now comes to the single molecule magnet. How this can become combining with the metal ion as well as the ligand. So that is inorganic properties combined with organic properties. So what are the single molecule magnets? So single molecule magnets are the paramagnetic exchange coupled clusters which are encapsulated by organic ligand, as I showed. This is the combining properties. Once it is magnetized, so this is the paramagnetic substance. If we applied field and cooling, so the all spin will be the same direction. Upon removal of the field, that spin orientation would be the same, and then it would slowly relax to the ground state, which is called the single molecule magnet or slow relaxation of magnetization. In this case, there is no intermolecular interaction is necessary. This is completely isolated molecule, discrete molecule. How can we characterize the single molecule magnet? The most important criteria for single molecule magnet would be the basic is high ground spin state and uniaxial magnetic anisotropy, that is called zero field splitting parameter. agent of these two factors, we can calculate the energy barriers, and depending on the energy barrier, how it will be act as a magnet. It will be permanent or the temporary magnet. So that can be calculated from this equation, where mu effective equal to mod of dA square for integer spin and for half integer spin in this equation. And so far, the highest energy barrier is 1815 Kelvin, but their blocking temperature is 20 Kelvin. So in order to perform the room temperature, so blocking temperature should be the above liquid nitrogen temperature. So that is the goal of the single molecule magnet. And so single molecule magnet not only depends on the U effective energy barrier, also the blocking temperature. What is the blocking temperature? Blocking temperature is the temperature at this point molecule can show the hysteresis. So far reported the organometallic mononuclear dysprosium complex, which shows the energy barrier 1541 Kelvin and blocking temperature is 80 Kelvin. It is above liquid nitrogen temperature. But one demerit is that this compound is unstable in air. So it is an air sensitive compound. Now goal is that how we can stabilize this molecule. So the experimental characterization for the single molecule magnet, basically we characterize by AC susceptibility and which is shows the, if it is shows the out of phase component in zero field or applied field. And also we can calculate the measure the hysteresis and energy barrier by Arrhenius equation in this plot, ln tau by 1 by t. So in the intercept that can be calculated the energy barrier. And what is the application? The application, as I said, this is high density data storage device, resistance, quantum computation, spintronics, and these are for the physicists. How SMM are different from the other magnetic substance? That's obviously comes. So for the ordinary magnet or traditional magnet, there is the random spin paramagnetic materials, and it is a bulk materials, multi-domains. But for the single molecule magnet, it is a single domain and same orientation of spin. Now, advantage of single molecule magnet over traditional magnet, as I said, so for this case, it is a single spin state, and we can easily modify the chemical modification by changing organic ligands that I will show, that I'm going to show you. And also we can synthesize this molecule at a room temperature, and the substitution of the peripheral organic ligand, this molecule would be more stable, and the magnetic core will be much more protected than the other traditional magnet. And also this molecule would be more stable in the air. And as we know, the our traditional magnet, if we heat too much, like above Curie temperature, the magnetism can lose. But in this case, depending on the organic environment, this molecule can remains their magnetic properties. And also this molecule can be stored in long time in air, this thing. So the first example of single molecule is the mixed valent nuclear manganese complex. Here, the central manganese are +4 state and peripheral manganese are the +3 state. And if we calculate from there for total spin state, it is 0, and the energy barrier is 61 Kelvin, and zero field splitting parameter is -0.61. So this energy barrier is very less. So then people think that how we can improve their properties by changing ligand as well as metal. So there are two different synthetic approaches. One is rational design approach and serendipitous approach. So what is rational design approach? Now in this approach, we can rationally design 2 coordinated pocket or 3 coordinated pocket containing ligand system like here, and we can modulate their nuclearity like dinuclear to trinuclear to tetranuclear. But above this nuclearity, it is difficult to control. So here, this design principle helps to isolate this trinuclear heterometallic complex, and which also shows the single molecule magnet, but energy barrier is very small. And what is this serendipitous approach? In this approach, it is difficult to get what product you are going to isolate, and sometimes it's not able to reproduce this product. Like here, nickel 12 cluster, this product is reproducible, but sometimes it's from the other product in between. So then we have to separate this product. So this is called serendipitous approach. So what is the significance of lanthanide over transition metal? Because lanthanide has high ground spin state. As I said, the magnetic anisotropy is also important, and some of the lanthanides are magnetic anisotropy. And because of the DF coupling, so this exchange interaction which increases the effective energy, total ground spin state for this complex. So therefore, the 3D combination is much more better than magnet of the 3D. So here are the different combination you can put for 3D and for a metal ions to get the different nuclearity and different magnetic clusters. Now, based on this concept, I am going to talk what I have done in my research career. Some of the results I am going to show, like nickel 3 Ln3 complexes, which is the different structural motif, and where nickel 3 dy3 shows single molecule magnet. In this purpose, we have designed the non-compartmental ligand. Non-compartmental ligand, it is not a SIP base, it is Manik based ligand. Here you can see the two different coordination site here. And in this case, utilizing this ligand successfully incorporated the lanthanide at the oxophilic nature and nickel. And we have first time isolated the hexanuclear nickel 3 Ln3 complexes. And this complex we have characterized by multitude of physicochemical technique. One of them is the single crystal XRD. Here you can see each ligand hold two metals, one lanthanide and another is nickel. And this is the core structure of this complex. An interesting aspect of this core structure is the defective cuban, heterocuban, cobalt dy2 nickel and dy3O4 cuban structure. And in order to check the magnetic properties, as I said, the coordination geometry is most important, and which can help to how it will be magnetically active or not. So here we have performed the self calculation, and that indicates the dysprosium center is 8 coordinated trigonal dodecahedron, and nickel is octahedral, distorted octahedral, 6 coordinated. And then we perform the AC susceptibility measurement. Here you can see the major Chi-T value are lower than the theoretical value. So which suggests that there is antiferromagnetic interaction exists between the oxo-bridge nickel lanthanide center. Then we check how this molecule, it is like a simple magnet or single molecule magnet. We check the AC susceptibility measurement. How among them only dysprosium 3 nickel 3 shows the in-phase and out-of-phase signal in applied field, and which suggests this molecule a single molecule magnet, although this shows very low energy barrier. Then we thought that what happened if we change this nickel by cobalt, because as you know, cobalt has the spin orbit coupling, and then utilizing this cobalt metal ion in the same reaction strategy, we have isolated the different structural form of this cobalt to dy4 complexes. And this is a interlinked defective cuban structure. And then we have characterized the magnetic susceptibility in the same way. And this, I'm going to skip this. And so here you can see also the major Chi-T value also a little bit higher than this of the expected value because of the spin orbit coupling. But unfortunately, this compound not shows the good magnetic properties. And then recent research shows that the impedance of the diamagnetic metal ion, which can increases the negative charge of the coordinated or bridging oxo ligand, and that stabilizes the ground state of the lanthanide, hence increases the energy barrier. Based on this concept, we have substituted the nickel and cobalt by zinc metal ion as a diamagnetic. And then we first time isolated the mu6 bridge, rare mu6 bridge zinc 3 Ln3 complexes. Here you can see the core structure of this complex. An interesting aspect in this structure, it is the double triangular topology, the dy3 as well as zinc 3. And the mean plane analysis says the 3 dysprosium center, which is encapsulated by mu6 carbonate bridge, and the 3 zinc center are bridging by the hydroxyl ligand. And the coordination geometry around the dysprosium center is 9 coordinated monocap square antigeometric, and zinc is the 5 coordinated and trigonal bipyramidal, although it is not magnetically active. Then we study their magnetic properties. Here you can see also chi-MT versus T as well as field versus magnetization, where this chi-MT versus T indicates the antiferromagnetic coupling exists between the lanthanide ion. And field versus magnetization indicates there is no saturation until 55 Tesla. So then we perform the AC susceptibility measurement, where you can see in this molecule only zinc 3 dy3 shows the zero field SMM behavior out of phase signal. And then we calculate the energy barrier, which shows the highest energy barrier among such systems reported so far in the literature. And for this case, we have to know the relaxation mechanism. As I said, how is the energy barrier and how molecule will be relaxed. If it is quickly relaxed, so magnetism will be lost. If it is slowly relaxed, then magnetism will be stored. So for this case, we have checked the magnetism relaxation mechanism, and this called the Cole-Cole plot. Here 3 types of relaxation mechanism are possible. But in this case, we have seen the distorted semicircle, which indicates that there is multi-relaxation process, including Orbach as well as Raman relaxation process. Unfortunately, the cobalt-2 terbium not shows the single molecule magnetic behavior. And also, the hysteresis shows the molecule is a single molecule magnetic nature. Now we have changed the ligand system for non-compartmental to compartmental seed-based ligand, where is the flexible ethanol group, which helps to expand the cluster. Here we have synthesized the first time triangular bend geometry containing cobalt-2 dy complex. And this complex, you can see this is isocyclic triangular arrangement of the 3 metal ions. And cobalt is the distorted octahedral geometry, 6 coordinated, but here cobalt is plus 3 state low spin complex. There is no contribution in this magnetic, only magnetism comes from the dysprosium center, which is 9 coordinated monocap octahedral, monocap square antigeometric geometry. And we have characterized the oxidation state of cobalt by bond valence sum calculation as well as magnetic characterization. In this magnetic characterization, where 1 by chi-m versus T yielded the effective magnetic moment is 10.68, which is correspond to the single dysprosium ion. And then perform the AC susceptibility measurement. Here also you can see in absence of field, zero field, which shows the out of phase signal nature of the single molecule magnet. Then we have calculated the energy barrier by Arrhenius plot, which is yielded the highest energy barrier reported so far. And this is the first example we have shown. And this relaxation mechanism for this case also, we have studied the Cole-Cole plot. Here we have seen this is a simple semicircle and indicates there is only one type of relaxation mechanism, which is called Orbach relaxation mechanism. And also perform the hysteresis measurement. Upon cooling, the hysteresis loop becomes bigger. So that's nature for the single molecule magnet. But for cobalt-2 terbium and cobalt-2 RBM case, this molecule shows the field-induced single ion magnetic nature in applied field and very low energy barrier. Now I am going to talk about how the simple lanthanide clusters show the single molecule magnet. In this purpose, we have designed the hydrogen ligand. As we know, hydrogen can show the tautomerization, this NH proton, and it will be increases the coordination number of this ligand. So based on this concept, we have synthesized this ligand and characterized and then react with lanthanide center in presence of base. We have first time isolated the rare example of seesaw geometry containing tetranuclear magnetic lanthanide clusters. And where dysprosium also monocap square antigeometric geometry, and magnetic characterization indicates there is the antiferromagnetic interaction exists between the oxo-base lanthanide ion, but until 7 Tesla, there is no saturation for these complexes. Then we perform the AC susceptibility measurement, which shows that at very low temperature under applied field, dysprosium shows the single molecule magnetic nature. What happens if we change the reaction condition? Can we incorporate more metal ion or less metal ion, or what happened? So based on this, we have increased the base strength and successfully incorporated the more number of metal ions in this ligand system and isolated the heptanuclear lanthanide cluster. In this cluster, you can see the two defective cuban are sharing by the common dysprosium center. And this is the molecular structure, how these molecules form, we have explained, and this coordination geometry, as well as the magnetic characterization. Here you can see the, the magnetic measurement, chi t versus t, is measure value are little lower than that of the expected value, also indicates the antiferromagnetic interaction. And AC susceptibility, only dysprosium shows the slow relaxation at low temperature. But this molecule has another interesting aspect, is the magnetic refrigeration only shows the gadolinium complex because it is isotropic in nature, more number of unpaired electrons. Now I'm going to conclude my talk that we have properly designed the manic-based ligand and first time isolated the nickel-3 Ln3 hexanuclear family, where nickel-3 Dy3 shows single molecule magnet. By changing the metal ion, keeping the same condition, we have isolated another structural motif of the cobalt-2 Ln4 complexes, where cobalt-2 Dy shows slow relaxation of magnetization at zero field. Upon changing the metal ion from paramagnetic to diamagnetic one metal, transition metal, we have isolated the rare example of mu6 carbonated zinc-3 Ln3 complexes, where Dy3 zinc-3 complex shows the highest energy barrier. By changing the ligand system from Manning base to Ship base, we have first time isolated the band geometry containing heterometallic trinuclear cobalt-2 complex, where cobalt-2 Dy complex shows the highest energy barrier so far reported, 88 Kelvin, but cobalt-2 terbium and erbium shows the field-induced single ion magnetic behavior. Proper design the hydrogen ligands, we have first time assemble the rare seesaw geometry containing lanthanide magnetic clusters, where dysprosium complex shows the slow relaxation of magnetization. By changing the base strength reaction condition, we have also isolated the heptanuclear Ln7 complexes, where dysprosium shows the single molecule magnetic nature at low temperature, but gadolinium complex shows the magnetic refrigeration. So what are the application of single molecule magnet, as I said? So this will be in the future application. So it can be used for hard drives like USB stick. We know everybody using the ATM every day, microphone that also contain the magnets. And also the future can be storage of energy, which is the most important in the future. So magnet can be helpful like for this. Also for the medical treatment like drug delivery, cancer therapy, and therapeutic application, as well as ladies are interested for magnetic nail polish, which can be stored long time for your magnet in the nail, as well also can be used for some people have pain in the back, so they can use the magnetic belt to relax. So finally, thank you all of you for your kind attention for my talk. And these are all my publication. I have published over 32 papers already. Professor Roy introduced, and now, yeah, I'm sorry. And now I'm going to acknowledge my PhD supervisor, Professor V. Chandrasekhar, for excellent guidance, motivation, and encourage for during my PhD as well as till now. That's why I'm here. Also, thankful to all of my postdoctoral hosts. They are giving me opportunity to perform research, and all collaborators for help me for some of the study like magnetic MOSBAR and also other institute for research funding, and CSR for during my PhD research funding. Also thank to Bankura College for giving me opportunity to present this work. And finally, thank to my family for the love, affection, and during my research career. And thank you to all of you.
Now is the question and answer session. I do not find any question in the chat box. So if anyone has any question, please feel free to ask, please.
Can I ask something, sir?
Sure.
Yeah.
Yes,
Okay.
Yes, sir, please.
Yeah, so I'm Sudhip Roy from BRC, and thank you for your very fundamental presentation. So although I'm not very much familiar with the inorganic synthesis, so I just want to know one thing, that in this inorganic-organic combination, right? So you have metal ion and then you have ligand. and
Yes.
you want to achieve certain properties like high ground state speed and so relaxation and all those things. And also you mentioned that intermolecular interaction is also important in deciding the overall magnetic property of your compound. So to design the synthesis, to design the complex, what is the most important thing? Means first you decide your metal ion that I will choose a porous metal ion to have a high speed, and then you go on modulating your ligand, or it is the other way. Means what is the most important thing to get a better single molecular magnet?
Yes, sir. So thank you very much for your interesting question. First thing is that no, for the single molecule magnet, there is no intermolecular interaction. That's I say.
Okay.
It is an isolated discrete molecule.
Discrete
so second
molecule.
thing is very interesting why we should do the single molecule magnet, because our traditional magnet, it is the solubility problem, and also I said how is the demerits. But for single molecule magnet, we choose first the spin state. As it is the more number of unpaired electron, it will be magnetically more active. So based on this concept, we choose the metal ion. And second is there is the uniaxial anisotropy. For transition metal, the uniaxial means zero field splitting, interelectronic repulsion, how they interelectronic repulse. And that helps to the effective energy barrier. So based on this concept, for the lanthanide ion, there is more number of unpaired electron, which is the more anisotropic than 3D metal ions. So that's why we choose the lanthanide better than the transition metal. And second thing, there is the DF exchange interaction. There is orbital spin interaction that you know. So which also helps to the increase effective energy barrier. That was the first motive. And then people synthesize the large nuclearity, like manganese 84 cluster also reported. But unfortunately, there is a lot of exchange coupling. This also not show the good single molecule magnet.
But
And
here also the interaction of the different atoms of the ligand, means although it is a single molecule, but that interaction can also change the magnetic property.
For the ligand interaction? Yes, that can help. That's why I showed you how the Mannich-based ligand to SIP-based ligand to hydrogen improve the magnetic property.
Okay. So that is the modulation of the ligand. So
modulation of the ligand as well as the combination of the metal ion. Not
combination of the metal. So combination of the metal ion is the first thing. That first you choose that okay, I will use 3D, and then how can you improve by modulating the ligand?
Yes, first we have to choose the metal ion, like that I showed cobalt has the spin orbit coupling, which is most important, can increase the spin state. And then also modulate their metal ion, and also ligand. Like some ligands can form low spin, some ligands can form high spin. Yeah, that's the way, sir.
Thank you.
Okay, thank you very much.
Dr. Mondal probably wants to ask something.
Yeah.
Yes, yes, go ahead, please.
So thank you, Dr. Joydev. It's a nice presentation, and it really reminds me my graduation days and inorganic complexes and all those things. So I have a question regarding that molecular magnets, what you said. Something serendipity approach or something you said. So unlike these aqua complexes of high valent metal ions and their simple ligands like cyanide and things, those molecular magnets are soluble in organic solvents, right? And then if you vary the solvent polarity or something, some other solvent parameters, then can you change the crystal field into those kind of molecules and accordingly their magnetic properties?
Yes, sir. Crystal field is important because, as I said, the zero field splitting parameter and anisotropy. So depending on modulation of the solvent, because as you know, if like that water, it is neutral ligand. If you use the cyanide, like that exchange molecule, like not only discrete molecule, there is another type of molecule, single chain magnet. So that is also a single molecular magnet part of, because of exchange coupling. So cyanide can bridge between the two metal ions, some metal form low spin and some metal high spin, and that way the exchange coupling also helps to improve their property.
So it is a combined effect of the ligand, solvent, and everything.
Yes,
so that way you can modulate that.
Yes, sir. Yes, sir.
Thank you.
Yeah.
If any other person has any question, please feel free to ask. Okay, probably there are no more questions, and thank you, Dr. Goura. for your fascinating lecture, which would be immensely helpful for our students. I hope some of our students will be motivated towards molecular magnetism as their future area of study and research. Thank you, sir.
Okay, thank you, sir.
We are going to start our technical session two within 2 minutes, just a minute. And now we have Dr. Jahur Alam Mandal among us. Dr. Alam has obtained his PhD degree from IIT Bombay. He has published his research work in more than 50 peer-reviewed and international journals. At present, he is working as Scientific Officer G in Radiation and Photochemistry Division of Bhabha Atomic Research Center in Mumbai. I would request Dr. Jahur Alam Mandal to deliver his lecture. Sir.
Thank you, Dr. Laik, for your kind introduction. And first of all, I'm very thankful to the organizer for giving me this opportunity to talk about the advanced spectroscopy techniques, particularly for the young students who, of course, in coming few years, they will be in the field of research. Maybe as the first speaker told about the magnetic molecular magnets and things. And there are many various fields. So I'm sure many of the students will be in research in coming years. So therefore, in today's lecture, I will talk about So can you see my screen?
Yes, sir, we can perfectly see.
Yeah.
Yes,
So
sir.
it is in full screen mode, right? Yeah, you can see the full screen, right?
Yeah, just hide this. There is
Yes, sir.
one.
Okay. So my topic today is advanced laser spectroscopy and its application. And the presentation will be mainly student-centric because the focus is the student and their future perspective in the research field. So I have made the presentation in such a way that, of course, any undergraduate student will be able to understand. And in case if you have any difficulty, please do not hesitate to ask questions. So to begin with, I have divided my total presentation into three parts. Number one is the background, where I talk about the basics of spectroscopy. And then the advanced spectroscopy, that is the thought process behind that advancement. And finally, some ultrafast processes, which is mainly the photo-induced or light-induced processes. And with this background in mind, I will tell you how, by using laser spectroscopy technique, we can monitor those ultrafast processes in real time. And again, using those advanced lasers, how we can develop new techniques where we can investigate some very kind of small spatial dimension like interface, how we can probe the molecules and see how they behave differently compared to that of their bulk and macroscopic phases. So as Professor Shomi Roy has nicely set the tone of the seminar today, and he had actually made my life easier by giving a brief introduction about the history of the lasers and its development and subsequent advanced techniques and its applications in various fields. So to begin with, let me tell you, particularly to the students, that we all are basically spectroscopists. We do some sort of spectroscopy, regardless of what we are doing and what is our age and things. So even kids do spectroscopy. So I will show you how. For example, we all have gone through that stage. So this boy, what he's doing is basically he is applying the principle of spectroscopy, and then he is interpreting what he's doing. So I will show you how. So the light, for example, so this is basically a lantern where from the light is coming and falling into this notebook. And from that, the incident light changes character. Part of it is gets absorbed and then gets scattered, and it falls into his eyes and gets detected. So this light source, and if we call this sample, and then if the eyes are the detectors, finally reaching into the brain, and the interpretation of the thing, what he is doing here is achieved by his state of mind and, of course, his intellect. So this is exactly what we do in spectroscopy. So there is a light source, there is a sample, and there is a detector. So his job, what he is doing is, as a spectroscopist, we do the same thing. So essentially, spectroscopy in general is as simple as this, and we all have done it, and we will be doing it. Again, let me give you some more examples. For example, if I show you this thing, all of you can say what it is. It is basically an apple which is masked by a certain force. How can we say that? Because nowhere it is written, it is just a picture. We can say that based on our experience, that possibly it was something like this. And then some sudden force has fallen to it and it has become masked like that. Let me show you another example. For example, this one. Again, you can guess what it is. It is basically an orange which has been masked by a heavy object or a car. And then a repeated moving over, running over onto that has transformed into this. So now, again, let us call this the initial state as the reactant and the final state as the product. And this journey, the sudden application of force and a heavy force going again and again into it, and the nature of the very nature of the initial object, they give different results. So if we call the initial as the reactant and final as the product, and the journey, that is what you are doing with it, and at what time scale these things are getting transformed, this is all, the basic principle is this what we use in spectroscopy. Again, a simple picture. For example, this one, if you take just a kettle, where from the water vapor is coming out, it is very familiar, and we have seen in the tea stall like this kind of picture. So again, you know that this vapor is coming because of some fire or some heat energy is given into that. So that transforms this liquid water into water vapor. So these are so commonplace that we do not even consider them what it is. But imagine that we are seeing it for the first time, that there is something, some liquid, and when we are putting some heat, they are becoming transformed into this kind of gas. So if we really understand that what is the nature of those things, what is happening by the application of force, then we have to do this spectroscopy. For example, we have to record the spectrum of the sample which is inside before application of heat, and then we will get this kind of spectrum. And then if you record the spectrum, which is coming out of this one, this gas, and if you record the spectrum, you will get this kind of spectrum. So you can see this has changed into this by the application of this. So naturally, something is happening into it. And anyway, what this spectrum means about the chemical nature of the compound, its state of, in which state it is present, and its interaction, mutual interaction, and all those things. So the basic picture is like this, as it is, we all know it, that this is the liquid water. You all know that water is a strongly hydrogen bonding and strongly interacting liquid. So they are mutually interacting and vibrating like this. And if we take the spectrum, for example, the IR spectrum or the Raman spectrum, then we will get this kind of broad spectrum, starting from 3000 to 3800 centimeters. And if we record the spectrum from here, you will get this kind of sharp band, which is basically the gas phase. Even it will be sharper than that, around 3700 centimeters. And then we can say that this band is very, very narrow, and this band is quite broad. So the molecules are strongly interacting, and they have a kind of very inhomogeneous structure. And as this band is very sharp, that means it has a very well-defined energy level. And so that means the molecules are not mutually interacting much. They are kind of isolated molecules. And this OH bond of the isolated molecule is stronger, much stronger than the bond OH bond over here, because energetically it appears at around 3600, 3700 centimeters, which is higher than that. So you can easily understand now, seeing this kind of spectrum, we can identify that what kind of molecular processes are taking place. Obviously now the question will come as a layman that where from I will get such kind of curve? Given a curve and having some understanding, I can interpret, that is fine. But how can we get a curve? So then comes that we have to do some experiment. Then only we can get such curves. So that's why for example, in the graduation or in the master degree, we mainly study, we try to understand the meaning of such curves. And of course, we do some practicals to get a sense that how we are doing the things, what kind of result comes, how to interpret it. So I am putting my perspective on that advanced spectroscopy in a similar approach so that you can easily connect with that thought process. So you have to do some experiment. So again, this is the simplest spectroscopy approach. You have some light source, you have the sample, you have the detector, put this sample over here, record the spectrum, put this one, record the spectrum, and compare it. Then if we do that, this is the Raman spectrum of water basically. See, from a very low frequency, around 100 centimeter inverse to 3800 centimeter inverse. So this spectrum, if you see, the molecules are basically kind of vibrating, their bonds are vibrating. So this region, for example, high frequency region around 3000 centimeter inverse. You see, this is a symmetric stretching of water molecule. So it can be any molecule. I have just taken a water because it is easy and simple to understand basically because it has only two bonds and not complicated. Although if we go into the detail aspect, it is extremely complicated. But anyway, today we are not discussing this. So here it is a symmetric stretching vibration, and here it is an antisymmetric stretching vibration, like one is stretching and other is compressing, and it is this way. So this is antisymmetric, and symmetric is like this. Everything is together. And then you have this band around 1650 centimeter inverse. You have the bending mode. So it is the angle is changing. And then you have this rotational mode over here. So the molecule, if rotates, then its absorption spectrum appears in this region. And here you have a kind of intermolecular hydrogen bond vibration. That means this hydrogen, which is bonded with a parent molecule and hydrogen bonded with the other molecule, that hydrogen bond also has the vibration. Of course, that bond is very, very weak. That's why it appears in extreme low frequency region. So these kind of understanding, partly you might have seen in your classroom, and of course in graduation you will be studying those things extensively, and in masters as well. So when you will complete your graduation, I'm sure you will all have the idea that what does spectrum means and what is their interpretation, how to look into things, and what does it tell about the chemical nature of the bonds and about their interactions. And this is the electronic absorption spectrum, just like the vibrational or rotational spectrum. These absorption bands indicates the energy required for the transition from one molecular orbital to the other, or it can be atomic also. So here also seeing the band position, we can talk about how the energy spacings between the different energy levels in a molecule. And depending on the changing environment, temperature, pressure, how these energy levels are get affected. So this kind of understanding really helps us to have a molecular view of the property of any material. And this molecular view, the view at the very, very shorter scale, it in the molecular level, helps us to explain the macroscopic or the bigger picture. So if we can have a continuous journey from the molecular level to the macroscopic level, and each and every step we can understand clearly, then basically we can play with the material as we wish. That is the purpose of all this kind of research. So these are quite simple, that by seeing the band weight, band intensity, change in band positions, how we can interpret the results. And then this one is the kind of very, very simple approach. Now, how we can think of the advancement of that approach, because this boy, what he is doing is, of course, the fundamental. And every development, if you look into the history, the development has started from its early previous steps. So one step ahead, and then next step, and then next step. That is what is called advancement. Advancement is not about a sudden kind of a violent discovery or something. It never happens. You have to go step by step. So if we think in that line, and if we have to think about the advancement of spectroscopy, then spectroscopy is having three components. One is the light source, another is sample, and the third one is the detector. So advancement means either there is an advancement in the source of the light, its nature, or there is advancement in the sample, maybe sample preparation, maybe the sample, which phase of the sample you are monitoring, and all those things. And of course, there may be technical development in the detector. So I will briefly mention about all those developments, and finally I will take you to some of the advanced technique, which is basically the state-of-the-art technique for using ultrafast laser spectroscopy. So to begin with, so this lantern has been replaced by some tungsten lamp or xenon lamp or something, which is still used as a light source in ordinary absorption or fluorescence spectrometer. And then we have the lasers, which are basically the light character is different than the ordinary source like this. For example, the light from this source or an electric bulb, it is a kind of diverging light. But the light from a laser, you can see the laser beam can travel even kilometers distance without getting diffused. So that is some special character of laser light. And apart from this kind of continuous light, laser can have pulsed character. That means you will have light for a very short time, and then there is nothing, another pulse of very short time, then there is nothing, like that. So that's why it is shown kind of dot, dot, dot. So these dots are basically when the laser is on, and this blank is basically when the laser is off. So these are kind of technical advancement which has taken place over the time. So I'll come into that again later. The same way, if you go into the sample, then you can have a sample which is solid in nature, you can have liquid, you can have gas. It is quite obvious, and it is as simple as that. And then you can have whether you are monitoring the bulk of the liquid or you are monitoring at the surface of it. This surface is basically very notorious because the thickness of the surface is just 1 or 2 molecular layer thick. In extreme cases, it is just 1 molecular layer thick. And in some other cases, it may go even few nanometers. So you can understand that monitoring an interface or the surface which has a thickness of just 1 molecular layer, that means you have to monitor that molecule itself. When you have a huge billions of molecules below that one. And of course, surface molecules will be different from the bulk molecule, but certainly they are not a completely different molecule. Their character might be changing. So there is a huge overlap of spectral features between surface and bulk. That's how it is extremely difficult to monitor these surface features. But today I will show you how to do that. And of course, some processes at the bulk of the medium. And of course, these things I am not going to talk. It is just for the sake of showing you the development I have just shown. So as a student, as a graduate student, you can clearly understand that these kind of developments happen step by step. And if we can understand the minute details, the each and every point, then really we can follow what is happening and what could be the future scope or future development, what is going to come ahead in coming days. So that we can clearly follow. That is the purpose of this presentation, basically to share with you some of the thought process which is going on in this field. The same way, if you look into the detector, then detector, it can be a simple photodiode, where if the light falls on this active component of that material, which is basically the diode, then depending on the intensity of the light, it will produce a current of proportional to the intensity of that current and light. And measuring that intensity or current, you can talk about how much light has fallen to that. And if you monitor a different wavelength, you will get the dots that suppose here light is very high, here light is very less, here very high, very less. So you will get a pattern. That's what is called the spectrum. Then it was realized that if you put a photodiode, you get just a one wavelength or one wave number point, one point. But a spectrum, it has a frequency distribution. So why not we use these photodiodes as a multiple photodiode, that is called diode array. So if I have, for example, thousands of photodiodes, and if the light different frequency falls on different positions, then within a single shot, I can record the whole spectrum. That is the purpose behind the photodiode array. So you can see there is a development. And then it was observed that these photodiodes, they cannot detect very, very weak signal. So we need something which can detect a very weak signal. Then came the photomultiplier tube. So what it is doing is the weak signal, which produces a very, very weak current, that is multiplied by a successive stage and electronically multiplied basically. And then final signal, you are getting a multiplied or intensified signal. The finally, what it is giving you, you can easily detect a weak signal. So that's what is photomultiplied, which is again a further improvement onto the photodiode array. And but the problem is photomultiplier tube, it is again a single channel detector. So that means you can detect only a single frequency. And then you have to scan over the multiple frequencies. So it is very time taking. Then the idea came that why not we to apply this diode array and the photomultiplier approach where the signal will be multiplied into one single chip. That is called charge coupled device or CCD. And then this CCD can detect very, very weak signal and a single short spectrum it can give. It can give you even the two-dimensional image of something very easily. So that is one of the very modern detectors used in various laboratories. And of course, this CCD has its advancement further, like for example, intensified. For example, whatever the intensity amplification you are getting, you can apply some additional component to get further amplifications and all those things. So this way, in the detector part also, one can use this advancement approach. Now coming into the chemical reactions, for example, again, this is a very well-known chemical reactions where tertiary butyl chloride is getting hydrolyzed and producing tertiary butyl alcohol. So I think in the graduations, all of you must have studied these reactions in organic chemistry. It is called nucleophilic substitution reaction. So where this ligand Cl- is going out and producing a kind of cation, and it is called the slow step. And then water molecule is approaching the cation, the central carbon, and forming this kind of intermediates, which is again releasing this proton and converting into the alcohol. So these steps are taught to us in graduation. In fact, I also learned this during the graduation. And it was told that this step is slow step. So this is the rate determining step. Remaining steps are very fast. So to be frank with you, during that time, I also learned this and I realized, I just remembered that, okay, this is the slow step, this is the fast step. That's how we all do. But we must ask the question that why this step is slow and why this step is fast. And if we know the answer, the next question will be, can we really monitor it? And if we have to monitor, what we have to do? Then we are really thinking consciously about the process. Because as a graduate, we have studied so many things. And a graduate level is enough to go deep into any subject and think deeply. Because if we look into the history, there are huge discoveries when they were at this level of graduation. So never underestimate your potential, but think in a step-by-step logical way, ask the questions which is not generally asked. And that will lead you to what you have to do. So if we ask the questions that why this step is slow and how slow it is and why it is fast, how fast it is, and how can we monitor those things, that is what we call in terms of chemical language is called the kinetics, dynamics, and the mechanism and all those things. So again, this is a technique which is a very well-known old technique where you can monitor the reactions. For example, when you are mixing this alcohol, alkyl chloride with water or some other acid or alkali, if you mix them, it will take certain time to react. So this is reactant 1 and this is reactant 2. If you mix them, and if you monitor by a spectrometer at different position, for example, it is flowing. So flowing takes time. For example, this is the 0 time where they are mixing, and then they are moving. So this passage on this path takes time. So if I monitor the signal over here, 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 there happens at different time. So monitoring the concentration of the reactant at different time can tell us that the reactant is more here, less here, and the product is increasing and increasing along this path. So that way we can get an idea that how fast the reaction is. But this approach can give us at the most, for example, millisecond or something. So millisecond means if you divide 1 second into 1,000 parts, so that one part is the millisecond, and during that time interval, the reaction is over, for example, or it is partially complete. Then one small improvement onto that was that you just put a piston here that is called stopped flow technique. So you stop the flow, means the reaction is stopped because spectrometer you are not moving in this case. It is fixed. So when the piston is moving away, the reactants are moving. That means that you are allowing the reaction to happen. And when the piston is fixed, no new reactants are coming from these two series. So by this improvement, we can measure the rate 1,000 times better. That means we can go even microsecond time scale, which is 10 to the power -6 seconds. So you can understand that simple approach, how it has revolutionized the measurement technique. But the point is, many reactions are even super fast. They happen in nanosecond, picosecond, even femtosecond times. And many such reactions are basically the photo-induced reaction. So as you know, for example, any reaction when it takes place, the reactant when it converts to the product, they has to face some kind of activation energy, most of the reactions. And it is this activation energy which determines the rate of the reaction. If the activation energy is very high, the reaction rate will be slower. And if it is very low, the rate will be faster. So obviously you can understand, if we put some light onto that, if we excite the molecule into the excited state, then from this state to here, the reaction almost there is no activation barrier. So it will be very, very fast. So this is called photochemical reaction because you are using light to activate the molecules. And from the excited state, it is coming down to the product state. Of course, it can come to the product excited state from where it can come down to the ground state. So what is happening here is you are bypassing the activation barrier by photo excitation. And that leads to the extreme fast rate of the reaction. And it has certain advantage over the thermal or the dark reactions, which is that many reactions in the dark phase is not possible, but by using the light excitation, it is feasible. You can achieve some selectivity, specificity, and of course, the time is very, very short. That means they are extremely fast. So these kind of ultra-fast reactions, which takes place in the time scale of femtosecond to picosecond range, certainly this kind of technique is not enough. So we have to think something different. And these kind of photochemical reactions are quite everywhere, basically, the world we live in. For example, the conversion of light energy from the sun into the chemical energy by the photosynthesis. And the vision process, for example, when light falls and we see the light, it creates the image in our retina, and accordingly the image is analyzed by the our nervous system. So what is happening here is that this kind of cis-trans isomerization takes place by the light. And this isomerization, that is the chemical reaction, transforms a chain of reactions and protein conformational chain, which eventually helps us to realize what is happening. So if you break down it into pieces, what appears is that this is the fundamental elementary state which leads to subsequent states. So all these steps are important, but if we try to understand them together, it's difficult. So we have to break down them into fundamental elementary steps, and we have to study them one after another, and then we have to connect and we have to give a complete picture. Same is the case in science and applications. For example, light-induced various processes are widely applied in science and technology, and of course, to overcome the energy crisis like solar energy conversion, the solar energy harvesting, and all these processes involves the basically mimicking the photosynthesis, where you are storing the light energy into a chemical form, chemical energy, and whenever you need, you turn on the switch, the energy will come in the form of usable form. So today's context, today's lecture context, our focus is how to monitor those ultra-fast processes, and how, once we know how it is happening, we can play with these processes and we can tune the way we want them to behave. But again, if we go into the detailed step-by-step approach, then what is happening is when you put the light onto the molecule from the ground state, it goes to the excited state. And in the excited state, as you know, the lifetime is quite short. It is at the most kind of, in general, nanosecond or something, even picosecond. So what they can do is that they can come down to the ground state by fluorescence. So just they will emit a light at a different frequency and come down to the ground state. Or they may not even emit the light, but just come down to the ground state non-radiatively, and they can undergo some electron transfer from the excited state to some other molecule ground state or excited state. They can give rise to the energy transfer. From this excess energy will be transferred to somewhere else, or the charge transfer process can undergo recombination and many other subsequent processes. So if we have to monitor, we can monitor this excited state, that how long it is surviving in the excited state. So we have to monitor this one, and we have to monitor the time for which it is surviving over there. And as I told, to do that, we need picosecond or femtosecond spectroscopy. So these are the kind of time scale, this is basically the Jablonski diagram, and these are the typical time scale of the various processes which happens in a molecule. For example, fluorescence, it occurs in the nanosecond time scale. This happens in the time scale of nanosecond to picosecond, and here it is around microsecond to millisecond. This is the typical time scale. And of course, from the higher excited state to the lower state, it happens in sub-picosecond or hundreds of femtosecond time scale. So these are the elementary states. And of course, we will see in complicated molecules how things can change apart from these elementary states. But it is helpful to look into the ultrafast spectroscopy with a view that how we can monitor these processes using these elementary states. So again, let's have a look back. What do we mean by femtosecond? So femtosecond means 10 to the power minus 15 seconds. That is, if you divide a second into 10 to the power 15 times, and then if you are taking one part of that, that is called 1 femtosecond. So in a simplistic way, if we consider that 1 minute is 1 femtosecond, then the age of the universe is basically 1 minute. So meaning is, if we break the age of the universe into minutes, then 1 minute is that much. If we break 1 minute into femtosecond, then 1 femtosecond is that much. So you can realize how short the time scale is. Naturally, to monitor such processes or such short time scale, we need some laser systems or some advanced light source which have such kind of short time features. So this short time feature is given by this kind of lasers, which is a short pulse laser. So I will explain briefly here what is this short pulse character. So short pulse means this light is coming. For example, if we monitor it in 1 second, let's suppose this is 1 second here. So within 1 second, suppose I have 10 or 20 pulses. Then 20 pulses per second means this laser is operating at a rate of 20 hertz. That means 20 times within a second. But that does not mean that 20 hertz means that during that period of the second, the light is coming. The light may come even for a much, much shorter time. So suppose this is a femtosecond laser, suppose 30 femtosecond or 50 femtosecond laser, then this light is there just for 30 femtosecond. And then there is nothing, complete dark. And then after few, for example, 0.1 second or 0.2 second, another pulse is coming of that 30 femtosecond duration. So the situation is like this. You have a light pulse of very, very short duration, and then there is nothing. Another pulse, there is nothing. Another pulse, and so on, so on. So this is called a pulse laser. And as you know, from that sample, you must have studied in 10th and 12th, of course, that what is power and energy. Power means energy per unit time. So as if you consider in 1 second, there is only 20 pulse, and most of the time there is nothing. So the power will be, average power will be very, very less. So this is very low. But if we consider one single pulse, then that pulse duration is only, for example, 50 femtosecond. So if we consider, although the total energy is not high, but if we calculate the power, so this small energy divided by 50 femtosecond, the time is very, very short. So if you divide with this small factor, the fraction is very, very high. So that comes around 10 to the power 12 watt, which is basically terawatt. It is huge. It is basically the power inside the core of the sun. So you can realize how strong these pulses are. And when it falls on a material, what it can do, it will create the plasma state of the material. So I will come into that later. So the point here is that you have the short pulses which are coming for a short duration of time, and then there is nothing, and then it is coming in successive states. So then, if we can play with this short pulse, and it is thanks to that laser technology, as I told in the beginning, it is the advancement of this technical aspect of the light source which enabled us to build this kind of advanced spectroscopy technique. So technical development and spectroscopic approach, they go hand in hand. And one development, once it comes, then the new openings opens up. And we need to think in an appropriate way that how we can utilize this advancement to solve some unknown problem or some new problem. So this short pulse, if we take as a perturbing thing to my sample, then depending on the pulse width of the laser, if it is nanosecond, that means 10 to the power minus 9 second duration of the pulse, then I will have a nanosecond time resolve or nanosecond kind of ultrafast spectroscopy. In fact, nanosecond spectroscopy was called ultrafast in the early days of ultrafast spectroscopy because that time picosecond and femtosecond laser was not there. And then with the realization in around 80s or sometime before that, this picosecond laser gives rise to picosecond transient absorption spectroscopy, and eventually the femtosecond, which is the 10 to the power minus 15 second, that gives rise to femtosecond. So it is a simple kind of smooth transition from nanosecond to picosecond to femtosecond. Again, I will show you some pictures in that line. And another interesting feature which I discussed here is the peak power. Because of high peak power, when it falls on a material, it creates a kind of plasma state of the material. That has a huge advantage and various ways to look into the material. And we will use those aspects again to develop a new kind of spectroscopy. And I will discuss about that also. So this is called the ultrafast spectroscopy, where the time is important. And this is called the nonlinear spectroscopy, that the material response becomes nonlinear. It is no longer linear. That is called the nonlinear spectroscopy. So, and then if we combine these two, we will get time resolved or ultrafast nonlinear spectroscopy. So you can see it goes step by step. So anyway, today I will discuss about these two things and not the lower one, that is the time resolved ultrafast nonlinear spectroscopy. But I am sure if you understood these two things, certainly you can realize these things also. It is not at all difficult. So again, the basics. What happens in ultrafast spectroscopy? So as I told you, there is a short pulse over here. So this pulse or light will go and excite the sample like this. So the pulse has passed through the sample. It has excited the sample over here. And these excited molecules will survive depending on their lifetime, for example, nanosecond, femtosecond, or picosecond, and they will die down and come down to the ground state. Then, as we have the short pulse, if we use another short pulse and pass through this excited zone, then this light pattern will change. Let's see it again. It has some pattern. If it passed through this one, depending on the state of the sample, its character will change. And if we see in the detector and seeing the change, we can say what has happened in the excited state. That is what is called pump probe or time resolved or ultrafast spectroscopy. So if we do it together, so I have a pump which will be ahead of the probe, and depending on how ahead it is, we will get the time. So let's see it, what is happening together. So it is going like that, and then it is just ahead of this probe pulse, perturbing the sample, and the probe is following the pump, and then it is getting its signal, which is varying with time. So then we get a time-dependent change in the probe pulse, which is called the time-resolved spectrum. So you can see here, for example, let us discuss with the nanosecond flash photolysis. Now it is called flash photolysis to just distinguish from the pump probe spectroscopy, but the basic principle is the same. So if I have a nanosecond pulse, this nanosecond pulse will create a perturbation of the sample for nanosecond duration only. And if I have an oscilloscope, which is the detector in this case, coupled with a photodiode, for example, then if it is synchronized with this laser, that my zero time is when this pulse falls on the sample, that is the zero time. And I have another light, which is the probe coming from here, will pass through the sample and then will be detected in a photodiode, and finally the photodiode current will be detected over here. And this is a kind of spectrum, kinetics will observe, and how in a nanosecond time scale it is changing. So from this variation, we can say how the sample has evolved in the nanosecond time scale. And this way, we can determine the transient spectral features. But by this nanosecond laser, we can determine only the kind of triplet state lifetime and few of the long lifetime singlet state, and most of the things we cannot. So naturally, some advancement is required. And in that process, once the picosecond laser came, nothing changed, only this laser was changed and some little bit was done here, and then it becomes the femtosecond, picosecond laser spectroscopy, which is a kind of technique which can gives you more information about the excited state at a shorter time scale. So as you can see here, this picosecond laser, it is, for example, 1064 nanometer light is coming out of this laser, which pulse duration is of picosecond. And then we can convert this light into different frequency by using second harmonic or third harmonic generation, some other nonlinear processes, and by which you can create the pump wherever you want to excite. And instead of a simple xenon lamp or tungsten lamp, what we are doing here is we are taking a part of this laser light and passing through this water, for example, some cell which is containing just liquid water, then you will get a white light. So this light and this light, they have a time correlation between them. And if you can monitor the time evolution over here by just delaying this light by some picosecond or some nanosecond duration, you can have the spectral response not only in picosecond, but in nanosecond region also. So essentially, by using a picosecond laser, you can detect the molecular processes in nanosecond as well as picosecond time scale. And then when it comes to femtosecond laser, just change the laser, nothing else. You get a femtosecond transient absorption spectroscopy, and you can monitor essentially all those processes. So you can clearly understand, once you understand the basic spectroscopic approach, understanding the advanced spectroscopy technique is not difficult, not at all. Only thing we have to follow the steps and what's happening. And if I show you a picture of our femtosecond laser system, then it is like this. So this is in terms of size, it is quite huge, but it is separated into different boxes. If you see here, this is box number 1, box number 2, and there is another box, it's 3, 4, 5. So essentially there are 5 boxes. So I'm not going into the details of that, what is there inside the box. But I can tell you what is happening inside the box. It is, and yes, of course, let's not forget this picture. This is the early stage of light source, which is, we all know it. And in the advanced spectroscopy, this source has been replaced by this one. Apparently, it seems complicated, and of course it is complicated, but the principle is as simple as that. And I will show you how it is. So if you see what is happening inside the box, then box number 1, which is this black box, is basically giving you a very, very short pulse. You see here, this one, this short red color pulse, which is around 50 femtosecond duration in our system. So it is extremely short, and it is 1 kilohertz. That means within a second, we have 1,000 such pulses. It is on, off kind of system. But this pulse energy is very, very low. With this low energy, we cannot do any experiment. Same way, if this lantern is at a very, very low flame, this boy cannot read what is written there. Same way, with this pulse, we cannot do anything. So what he will do? He will raise the intensity or the flame. Here, we have to do the same thing. But how can we do that? If we just amplify this one, just go on rising it, then the material where it will fall, I told you that because of its very short pulse character, it will create a plasma. It will destroy everything. So we cannot really amplify that way. So what we do is, this high power is coming because of its short pulse rate. So let's change the pulse rate. So that's what we did in box number 2, here, this part. So what we did is, this one, we stretched in time and made it like this. It is a very stretched, and if you stretch it, the total area under the pulse will be same. So it becomes very short, very weak. Then its peak power is less. Now let's amplify. It is higher, but it is such a broad pulse, some high power, but this will not damage the material, because anyway, the total energy of this pulse is less, and the power is less also here because the pulse is quite stretched. Then what we are doing here, after stretching, this is the stage 3 over here, 1 amplifier. And then we are not happy with this one. We want to amplify it further. So we use another box, box number 4, which is here, background. We amplified it further. So we have a huge broad pulse. But again, this big time or the long time duration is not going to help us to observe the short phenomena or fast phenomena. So we have to compress it back. So that's why what we did in box number 5, that means this part of the box. And finally, what we observe is this kind of intense short pulse. So you can see here, this was what was given to us over here, and we transformed it into multiple stages like this. So if you combine all these, it is nothing but raising the flame of this lantern. So the basic principle remains the same. However, if you see the life of the researchers who does handle this kind of systems, their life is not as simple as this boy. In fact, I am jealous of this boy. If you see, he is so focused on his study. He does not even bother what is happening in his lantern. Whether once he raised the flame, that's all. He is totally focused. But these researchers, their life is not as simple as that. It takes tremendous amount of effort to really maintain the laser and to have the quality of the beam, of this beam, to really do the experiment. And this is the beam here. You can see here one faint beam here at the circle of center of that green circle. So that is the amplified pulse. You see, it looks so faint because the average power is very, very less, because the pulse is very, very short in time. So in terms of average power, it is less, but in terms of peak power, it has the ability to destroy any material. And by the way, he is Subhadeep Roy, who is my PhD student, and it is basically through whom I came in contact with the Department of Chemistry, and I was invited to give a talk in that. So it is basically he who introduced me. And I must say that I'm very fortunate to have such kind of highly enthusiastic and energetic student. Basically, whatever I am presenting, and I will be doing some of the work of Subhadeep and Nishit. So these are the result of their hard work. I am just presenting, believe me. So this kind of hardworking motivations and the curiosity is the key to do some leading research. So coming into some of the chemical systems where we can apply these kind of techniques and see what is happening here. Oh, I'm running late. So this is a chemical system which is basically a molecule having two parts. One is the anthracene part, and another is the aromatic part, heteroaromatic component. So when we excite this molecule by using 400 nanometer light, we are exciting this part of the molecule, but we are getting the emission from this part. So even if you ask a layman what is happening here, they can tell that although we are exciting here, something is happening here, and the energy is coming here, and the emission is coming from this part. So we also said the same thing, that there is the energy transfer from this to this. But what is the rate of this energy transfer? So how do we know? Just seeing that which part of the spectrum, where it absorbed and all those things, seeing the simple absorption and emission spectrum, we can say that there is a transfer of energy. But to monitor such spectrum, rate of that energy transfer, we have to monitor the dynamics using this technique. And when we do that, what we observe is, this is the spectrum, for example, 500 to 1000 nanometers region. So you see the black curve, it is going up in this region and converting into this, finally, this red curve. And the time is 0.2 picosecond, that is 200 femtosecond, 1.5 picosecond, that is 1500 femtosecond, like that, up to 24 picosecond. So within this duration, it has almost converted and come to a kind of long lifetime state over here. Further decays happens in 200 picosecond or something. So you can see these processes are happening at a time scale of 200 femtosecond, which is really, really fast. And by monitoring these characteristics of this state, as I told you for water, seeing the band at around 3700 or 3300, we can say whether it is in the gas phase or liquid phase. Seeing these positions, we can say which part of the molecule is giving this signal. And when we determined the lifetime, we found that there is a fast component of 5.5 picosecond, followed by a slow component of around 1 nanosecond. And that we assign. And then again, when we monitor this process in various other environments by changing the solvent, we observe that it shows some solvent dependence. Like as the solvent becomes more viscous, the lifetime gets shorter and shorter, longer and longer. And that means the rate becomes slower and slower. So we propose a mechanism like this, that this is my initial molecule over here. So when we excite it by 400 nanometer light, it quickly goes to the excited state within femtosecond. And then it undergoes some kind of transformation, some conformational change in its excited state. And the energy in that, during this conformational change, the energy gets transferred from this part to this part of the molecule. And then finally, we are getting emission. And this transformation is basically happening at a time scale of 200 femtosecond. So you can see by using this kind of spectroscopy approach, we can monitor the ultra-fast energy transfer. So again, if we compare with the basic picture I have shown you in the first slide itself, you can easily connect that this apple is nothing but the initial state of the molecule. And this excitation, whatever we are doing here is basically we are hammering the apple. And once we do that, it's shuttered into this shape. And although by some fast camera, we can see this, what is happening. But in this case, the fast camera is basically the technique, the spectroscopy technique, by which we found a time scale of 200 femtosecond and to convert it into this. So this journey is what is happening here, which in this case, you can observe by fast camera. That's all in the energy transfer. Same way, electron transfer is another fundamental elementary steps in many, many chemical reactions. So here I have shown a typical example of beryllium. When excited, it transfers its energy into another cationic micellar component. And there, when we monitor these components, we observe this kind of change. There is a spectral decay in this region, and there is a spectral rise in this region. And seeing the spectral position, we can say that this is coming from beryllium cation radical, basically cation radical, because the electron has been transferred, and this is from the beryllium singlet state. So what is happening here is when we excite this one, it quickly transfers its electron to this one, and it gets converted into a radical. And exactly that's what we are observing here. So this spectrum is not just like some kind of dead curves, but they are basically the live things, which tells us what is happening on the system. So this way you can monitor the electron transfer processes as well. And here another example, the photoisomerization reaction, I will show you. So this is a kind of aryl azo compound, which is having a double bond, nitrogen-nitrogen double bond. So when you excite with light, they convert it into cis form. This is called isomerization, but as it is happening with light, it is called photoisomerization. And there again, you see this kind of spectral evolution is there. It is rising here, it is decaying here. And when we feed this component in the lifetime, we observe that it is over almost less than 2 picosecond time scale. That means the lifetime will be less than 0.3 or 0.4 picosecond. It is extremely, extremely fast. And we propose that what is the mechanism and all those things. So I'm not going into details, but this is the essence of using ultrafast laser, how you can monitor the fast processes in a time scale of sub-picosecond. Now I will go into another aspect of the ultrafast laser, that is the high peak power. And using this approach, I will show you how we can monitor the molecules at the surface. So here again, the peak power being high, it has this kind of features. And when we excite or put this light into a kind of material, when the light intensity is low, this kind of transition happens. Either it can lead to absorption, it can lead to scattering, and all those things, which are essentially mostly linear processes. But when the light intensity becomes very, very high, of course, these processes happen. Apart from that, another new process takes place, which is the two photons simultaneously interact with the material, and they create a virtual state, and the molecule can emit light from that virtual state. And this is called second harmonic generation. So that means if we try to understand it simply, the light intensity is so high that two photons combine together in a coherent fashion and produce some new light whose frequency is double of that two incident light. And this phenomenon has some another interesting feature is it does not happen anywhere. It happens only in the region or only in the medium which does not have inversion symmetry. That means in a symmetric medium, it does not happen. So what do I mean by symmetric medium? For example, if you take a glass of water, the bulk of the medium is symmetric. Because here, if I, for example, consider my reference point, so left, right, and top, bottom, everywhere, the environment is similar. So it is symmetric with respect to a point in a macroscopic scale. So that is called the inversion symmetry in macroscopic scale. But at the surface, if you consider the top layer, top side is air, bottom side is water. So it is not symmetric, the environment is asymmetric. So now, if we apply this principle into that surface, so then my some frequency will be generated or second harmonic will be generated only from the surface, not from the bulk. There will be no signal. This in turn tells us that if we can use this as a spectroscopy, then I can monitor the surface molecules by seeing into this signal, if I can separate them physically. That is exactly what has been done. And this was done in 1993, that for the first time, and it was recorded, the water spectrum from the liquid water surface. And this was the spectrum. So you can see the bulk water, it has the spectrum like this. For the liquid, it has this kind of, along with that, another feature is there, which is a sub feature. So this was a sign that the topmost water molecules has a different vibrational features corresponding to different species. That is, the topmost OH is pointed towards the air and it has nobody to form hydrogen bond with this OH. That's why it appears at the high frequency region. But here, it is strongly interacting with neighboring water molecules and no such free OH region is there. So it gives us a molecular picture of how the molecule is sitting there, behaving there, and all those things. But this is the story in 1993. This was reported first time. And eventually, again, it undergoes further development. And in 2007 around, 2009 around, there was another spectroscopy technique which is based on that conventional spectroscopy, which is called the heterodyne detected vibrational sound frequency generation, which can detect the topmost water molecule not only by their spectrum, but how they are sitting. Actually, it can tell us how they are sitting like this or that, like that. And this spectroscopy was first discovered in Japan, and as well as almost simultaneously, we can say, as well as the University of California. And during that time, I was a postdoc in Professor Tahara's laboratory in Japan. And I got introduced to this technique through their laboratory. And that technique is well ahead of the earlier technique, that is some frequency generation. So this is then I returned from Japan and developed this technique in BARC. And this is the laser system, as I have already shown. By using this laser system, one part we can develop, or we can have the ultrafast spectroscopy. Another, we have the nonlinear spectroscopy, that is the some frequency generation. So now I will discuss some of the results on water surface. But again, the basics. If you see, this is my laser, which is the light source. This is the sample, this is this, and this is the detector, this is this. So you see, the basic principle or the basic thing never changes. It always remains the same. So when we look into such spectroscopic things, or when we read any scientific paper or anything, if we try to analyze the things as per our basic understanding, then things become very, very simple. So this is the spectrum what one can get by using this advanced heterodyne detected vibrational some frequency generation spectroscopy. Here the spectrum has not only just the kind of band shape, but it has sign. For example, this part is negative and this part is positive. So this positive 3700 band indicates this kind of water structures or water features, whereas the negative part indicates these kind of vibrations at the surface. So essentially, as if you are sitting on water surface and seeing molecule by molecule what is happening at the surface. So that is the essence of HDFS. And this signal is called imaginary K2 spectrum. I am not going into the details of that, how we observe the spectrum, get the spectrum and things. But although the name is imaginary, the spectrum is not really imaginary, it's real. And we can really see what is happening. And as I said, this has another advantage that we can see how the molecules are oriented. So suppose these molecules are oriented like this, their hydrogens are up. Then if we can get a signal like this, when they will be oriented down, we can get a signal like this. So the signal will change. So seeing the change in signal, we essentially talks about how they are oriented. And then we quickly apply this technique into biological lipid interface. And when we do that, of course, the lipid is simplified system. We did not apply into the actual cell or things because then it will be extremely complicated. So when we do that, we observe that when the lipid molecules are cationic or positively charged, we have a negative band over here. And when the lipid is positive, we have a positive band, when the charge of the lipid is negative, we have a positive band. Positive band means water is oriented like this, and negative band means water is oriented like this. So that's what we reported for the first time, that what happens to water orientation at charged lipid-water interface in 2010. And then in 2012, we talk about the orientation of water when the lipid is not only just independently positive or independently negative, but when positive and negative are present together, what happens? And then we saw that around the positive part, we have the H-up-oriented water, and around the positive part, that is nitrogen N+, we have H-down-oriented water, and around the negative part, that is the phosphate, we have H-up-oriented water. So this kind of distinct structure around the deuteronic lipid-water interface. So that we discussed in 2012. And then to move in that direction, for example, not only the pure lipids, if we apply some other molecules which is biologically relevant, then what will happen to such kind of lipid interfaces, because it is fundamental to the structure of the cell and the cellular processes. So I took upon one aspect of that. Today I'm not going into that protein and other things. One aspect, one very, very simple molecule, which is this molecule, basically trimethyl amine enoxide. It is observed that this molecule plays a crucial role in the pathogenesis of cardiovascular disease, that is the heart disease. So as you know, the patients or the persons with the age, our arteries becomes narrower and thinner because of the deposition of this kind of fatty materials inside the inner wall of the artery. And doctors suggest that it comes due to kind of a food habit and lifestyle. And it is associated with the kind of food we take. So for example, lots of energy-rich and kind of for example, egg and non-vegetarian foods and energy drinks, which contains this kind of choline component, they, when get metabolized, produce this kind of molecule. And this molecule is responsible for subsequent deposition of fat and ultimately leads to fatal condition. So my objective here is that how this simple molecule can affect the inner wall of the artery so that this kind of lipids gets deposited over here so easily. So in doing so, again, let me tell you, I did not take the real arteries. I took simplified system, which I have already studied, and form a kind of monolayer on water surface, because inside the cell you have water, and this is a bilayer. So bilayer is basically the double of monolayer. So I took a monolayer so that the science does not change, or we can get some insight about what is happening. And then we found that when we put the TAMO molecule, it changes the signal, water signal. Its signal is increasing. So this increasing signal is assigned to the change in electrical environment on the membrane surface. So that we discussed in those papers, that how the orientation of TAMO, depending on the charge of the lipids, can disturb the interfacial electric field at the membrane. And then finally, I will talk some of the recent work on ion set interface. So for example, at water surface, how different ions can go there and sit there. And this is very interesting, actually, I must share with you. In around 2007-8, during that time, I first encountered such kind of work, where it is shown that ions can go to the surface of water favorably. They happily go and sit there. So according to classical understanding, it was a bit surprising that how a charged ion will go to surface of water, because it will go inside the water. If it is something highly hydrophobic or amphiphilic kind of molecule, then only they will go to the surface. So at least I was very surprised, and it was hard to believe initially that ions indeed can go to the surface and sit there. And then the some frequency generation spectroscopy is one of the ideal experimental technique to probe such things. And over the years, it has been shown that highly polarizable big size anions like I minus, iodide, and many others, they can go to the surface and sit there. Rather, they prefer the water surface. And they can even create a kind of layer of ions so that the surface becomes negatively charged, so the water molecule gets oriented around ions, as if it is the amplifier. But what happens when this ion is strongly hydrating, for example, carbonate, or for example, fluoride, or other strongly interacting ions? So it is said that those ions do not go to the surface. They remain in the bath. But that is a very qualitative understanding that we can say by measuring the surface tension as well. But having a molecular spectroscopy technique of such advanced character, we must be able to tell something deeper feature of those ions at the interface. And that's how we get motivated to investigate about the chloride and carbonate. And Subhadeep played a lead role to investigate these aspects. So what we observed is this kind of ions is when it is in the interfacial region at the very near to the top surface of water, and it affects the spectrum this way. The overall intensity does not rise, but the band becomes broader and broader. So based on that, we propose that cosmotropic anions, like strongly hydrated anions like carbonate, fluoride, they do not form a kind of charged surface or kind of electric double layer, but they perturb the structure of water by forming strong hydration or hydrogen bonding with the surface water molecule. And then again, we studied some other ions like that, and we observed that there too, depending on the nature of the ion, they affect the hydrogen bonding patterns of the ion and can create the orientational perturbations of the surface water molecule. So I'm not going into the details how they are perturbing and all those things, but certainly this gives a qualitative sense that how we can use that kind of spectroscopy and can see the molecules, how they are affected. Because these affected waters plays a key role. For example, if we take the case of atmospheric chemistry, the cloud formation and all those weather and things, it depends on the character of the aerosol, the ion content, and the interactions of the surface water with the organic or amphiphilic molecules at the surface of the aerosol particles. So it has a fundamental importance about the air quality, cloud formations, and many other aspects. So it is, and of course in biological field of, as well. For example, in cellular systems, we have ion channels and things. So ionic effect on cell membrane interface is also very, very important. So how these ions behave at the interface is the focus of this research. And then another aspect is the pollutant, which is basically everywhere, and even in this modern world, because of industrializations, the pollutant is affecting our health as well as all aspects of life. And fluoro compound is one such pollutant which is ever existing. That means it is non-biodegradable. Once it is released into the environment, it will stay forever. And that leads to a serious threat to the human health. So we decided to see how this fluoro compound behaves at water surface, how it affects the lipid molecules, how it affects the other surfactant molecules. And for example, if it is released in a particular place, how it's spread over to different parts of the country and of course, outside the border of the country, all over the world. So there, its surface behavior plays a key role. So when we investigate this molecule by using surface spectroscopy, we observe that this molecule, when interacting with this kind of non-fluorinated compound like heptanoic acid and octanol, it has a distinct behavior. In one case, for example, heptanoic acid, it has a this kind of small change in the spectral features as if nothing has happened. So all the alcohol molecules, all the acid molecules are sitting at the water surface as if this one has nothing to do. Then when we took this one, just we change the head group, acid has become alcohol, then we see that the alcohol molecules are vanishing from the surface. The signal has reduced in presence of this perfluoro compound. Then we take some long chain molecules. For this, no change, even for the acid as well as for the alcohol. Then we propose that this molecule has a very interesting character. When this is alcohol, they do not form such kind of strong interaction with this molecule. And as this is more hydrophobic, it prefers to stay at the surface and remove these molecules from the surface. Whereas when this is acid, it forms strong hydrogen bond with the head group of the this fluoroacid, and both of them are staying at the surface. And when these molecules, hydrogenated compounds, are long chain, then this acid molecule is removed from the surface. So it is in water. So whether they are at the surface or they are in the bulk of the water, they are transported from one place to the other in the sea surface, for example. It is dramatically different. So that this kind of molecular mechanism or understanding help us to understand how a fluorinated pollutant can be transported from one place to the other, and what is the molecular mechanism of such kind of transport. So with this, I am at the end of my presentations, and I would like to give you 3 messages, particularly to the students regarding this presentation. And the number 1 is, laser spectroscopy is a rapidly evolving field of research. And number 2 is, time-resolved ultrafast spectroscopy is unbeatable when it comes to monitor fast reactions. And number 3 is, interface selective VSLG and its time-resolved variant are state-of-the-art spectroscopy approaches for surface science. So with this, I finish my presentation. And of course, it is whatever I have presented, it is the hard work of my students and my co-workers, and of course, my colleagues who have helped me in various ways in different forms to do this kind of work and to develop such kind of spectroscopy technique in the years. Thank you very much.
Now is the time for question and answer session. I do not find any question in the chat box. If anyone has any question, please feel free to ask.
So I will be very happy if students ask some questions, because it is solely focused on the students.
Yes, sir. It seems nobody has questions at this moment to ask. However, I would be happy to forward such questions to Dr. Alam Mondal if you send them later.
Sure, I'll be very happy to answer them, and of course to interact with them in future in case they would like to know more about it.
Thank you, sir, for your captivating lecture on laser spectroscopy. I'm sure it will be immensely helpful for the students who are contemplating research work in this advanced area of chemical science. Thank you, sir.
Thank you.
Now I request Dr. Mridula Acharya, Assistant Professor of Chemistry in our department, to deliver the vote of thanks and conclude the webinar.
Sir, am I audible?
Yes, yes, perfectly.
Okay. On behalf of the organizing committee, myself, Mridula Acharya, is here for vote of thanks. I hope that I will be able to send the true feeling of the department that we hold for our guest through this electronic media. First of all, our honorary guest, Dr. Joydev Gowda and Dr. Jahur Alam Mondal. Sir, a big thank you from the core of our heart, not only for the reason that you have delivered wonderful speech, it is for the reason that you have inspired our beloved students once again to be proud as a member of the beautiful world of chemistry. They have already chosen chemistry as their subject, having some beautiful dreams in their mind. But in this pandemic period, There are different thought of fear, anxiety coming in their minds regarding their future. This often reflects when we interact with them. I hope that they will be able to dream once again and find their way out. I hope they will fall in love with this fascinating world of chemistry once again. I would like to thank Dr. Fotik Boron Mondol, the patron of this webinar, for his constant encouragement. Thank you, sir, for your inspiration. Next, the president of the organizing committee, Dr. Shomir Kumar Rai. Sir, thank you. These two words are not sufficient to express what we feel for you. We sometimes forget that you took retirement on 2013 and we do not want to remember this. Because whenever we find any difficulty, maybe with our departmental proceedings or about chemical society, the first name came in our mind is you. And we are not going to change that. We know you will always be there with us. Please stay safe, healthy, and energetic as you are always. Dear audience, you will be happy to know that we have two other guardians as our senior faculty members of the department, Dr. Vivekananda Mohanty and Dr. Debashish Bandyopadhyay. Thank you, sir, for always being there with us as our mentor. Next, our convener of the webinar, Dr. Manoj Kumar Layak. Sir, no one of the department can handle online mode better than you. And you have two strong supporters, Dr. Shogoto Sai and Dr. Shantanu Mondol as joint convener. You are friends before you are colleagues. Dear audience, we have a very energetic joint secretary of the webinar, Mr. Mohendra Ghosh. We hope in near future, we will be able to organize many more webinars under his able guidance. Being the junior most member, he is very near and dear to all of us. And at last but not the least, our students, thank you all for your patience. You know, one thing maybe sometimes you find it difficult to maybe helpless without us, but the truth is that we are nothing without you. We wish all of you a bright, fascinating future. You are the flag bearer of this prestigious department. Department of Chemistry, Bankura Christian College is the name of an emotion, name of a culture, name of a heritage. And we all are very proud to be a part of this institute. Thank you all once again for being with us in this webinar. Thank you.
Thank you. With this, we are concluding our webinar. Thank you all.